Hello, it's Richard Hammack's Calculus 1. We are in part 5 of the course on integration. This is lecture 44a, Integration by Substitution. Most recently, we talked about the fundamental theorem of calculus. It came in two parts, part 1 and part 2. Part 2 was the most useful version. It told us that to find a definite integral, we need to find an antiderivative, an indefinite integral. So success in using part 2 involves knowing lots of integration rules. Our plan for today is to learn a new integration rule called the substitution rule. It's an integration formula based on the chain rule for derivatives. In essence, it's the chain rule in reverse. We'll break this up into three parts. Today in lecture 44a, we'll talk about substitution in indefinite integrals. In 44b, we'll look at more examples of substitution. And in lecture 44c, we'll talk about substitution in definite integrals. Let me begin by reminding you of our integration formulas that we've learned so far. For instance, we had the power rule for integrals. The integral of x to the n dx equals 1 over n plus 1, x to the power of n plus 1, plus c. I'm going to make a slight change in this and our other rules. I'm going to change the variable x to a u. So wherever we see an x, we'll just switch that to the variable u. So the formula now reads the integral of u to the power of n du equals 1 over n plus 1, u to the power of n plus 1, plus c. It's the same formula, we're just using a different variable. And we'll do this for all of our integration rules. For instance, the integral of e to the u du is e to the u plus c. The integral of cosine u du is sine of u plus c, and so on. We also had these three rules. I've changed all the x's to u's. By now you've had lots of practice in using these rules. Today's goal, as I said, is to learn about the substitution rule, the chain rule in reverse. And the idea is that the substitution rule, combined with the formulas on this slide, greatly expands the types of functions we can integrate. The situation is very much analogous to when you learn the chain rule for derivatives. You'll remember that you derived a list of derivative rules, and then you learned the chain rule. And the chain rule, applied to the rules that you already knew, greatly expanded the types of functions you could find derivatives of. We'll do exactly the same thing today with the substitution rule. It's a new rule that, combined with the rules on the slide, will greatly expand the kinds of functions you can integrate. So let's get right down to it. Let's run the chain rule in reverse to derive the substitution rule. We'll do it on this slide, and we'll put our new rule at the bottom. In the setup, imagine you have a function, big F, for which big F prime of x equals another function, little f of x. In other words, big F of x is an antiderivative of little f of x because when you differentiate big F, you get little f. Remember the chain rule? It says that the derivative of big F of g of x equals big F prime with g of x plugged into it times g prime of x. Now, in our setup, big F prime equals little f, so let's change this big F prime right here to what it's equal to, little f, and we get dx of big F of g of x equals little f of g of x times g prime of x. What this equation is saying is that big F of g of x is an antiderivative of little f of g of x times g prime of x, because when you differentiate big F of g of x, you get little f of g of x times g prime of x. So writing that as an antiderivative, we get the integral of little f of g of x times g prime of x dx equals big F of g of x plus c. You can check this formula by differentiating the answer big F of g of x plus c. And as you see up here, you get little f of g of x times g prime of x. You get the integrand. So you know this is a correct formula. This is the chain rule in reverse, right here. Now it's not quite the substitution rule yet because we're going to first make some simplifications. What we're going to do is wherever we see a g of x, we're going to replace that with u. In other words, we're going to let u equal g of x. And I'm going to put this over in a box on the side. U is equal to g of x. So every g of x here and here, we're going to replace that with a u. But we also have a g prime of x dx right here. We got to deal with that somehow. What we're going to do is follow the consequences of setting u equal to g of x. If you differentiate this function u equals g of x, you get du dx equals g prime of x. We're next going to multiply through by the differential dx to get du equals g prime of x dx. So if we let u equal g of x, we get du equal g prime of x dx. Now let's substitute these boxed equations right here into this formula. First of all, where we have the integral of f of g of x, that's going to be the integral of f of u, because we're letting u equal g of x. So we get the integral of f of u when we make this substitution. Now the next thing that we have is a g prime of x dx, and look over here in the box, g prime of x dx equals du. So all of this is going to be replaced by du. Now on the other side of the equation, we have big F of g of x, and g of x equals u. So that's a big F of u, and then we add on the c, and we get plus c. So look what happens to the chain rule in reverse here when we make the substitution u equals g of x and du equals g prime of x dx. This complicated looking integral changes into something simple. The integral of f of u du equals big F of u plus c. The substitution rule is merely going to state that this integral equals this one when you make the substitution u equals g of x. It says this equals that. We'll put it in a box right here. This is the substitution rule. If u equals g of x, as it was here, then this integral equals this one. The integral of f of g of x, g prime of x, equals the integral of f of u du. That's the substitution rule. Now what this does is that it takes a complicated looking integral right here. It's very complicated, and it changes it into something simple. So imagine you had an integral that was complicated, and you're trying to find out what that integral equals, and it doesn't match any of the rules that you know. The substitution rule says that if you could make a substitution u equals g of x and convert this complicated integral into a simple one, then your work might be easier. This integral of f of u du, it might be something that you have an integration rule for, whereas you didn't have one for this. That's the power of the substitution rule. Now, it may look a little complicated at first on this slide, but when you start to look at it examples, you'll see that it's actually really simple. So let's do that. Let's look at some examples of the substitution rule. an example of how converting a complicated integral like this one to a simple integral would mean that you could evaluate an integral easily. For our first example, consider the integral of cosine of x squared plus 3 times 2x dx. This is a complicated integral that doesn't match any familiar integration rule. Let's see if we can use substitution to convert it to a simple integral that we do have a rule for. The way to proceed is to think about your familiar integration rules and which one this most closely matches. It's got a cosine here, so it looks something like the integral of cosine u du. Let's see if we can make a substitution that converts this complicated integral into the simple integral of cosine u du. And if we can do that, we've got an answer because the integral of cosine u du we know is sine of u plus c. Over here, we have an x squared plus 3 plugged into the cosine, and that suggests that our u should be x squared plus 3. So let's write that down. We're going to make the substitution u equals x squared plus 3. And that looks good because that's going to convert this to the integral of cosine u. But then we also have the 2x dx right here. And we'd like to replace that with a du. But we've got to be careful. We've got to make sure that 2x dx really does equal du. To see whether or not it does, think about our u equals x squared plus 3 and take its derivative. Du dx is 2x. And now multiply through by the dx. And you get du equals 2x dx. So this 2x dx that's right here, you can see it really does equal du. So now we can make these substitutions. We get the integral of cosine of u when we replace the x squared plus 3 with u. And then there's a 2x dx right here, and that equals du. So now we've converted this complicated integral into a simple integral, the integral of cosine u du, and we have a formula for that. It equals sine of u plus c. And we're almost done. Originally we had x's in our integrand, so we need x's here in our answer. But of course u is equal to x squared plus 3, so you just replace that u with the x squared plus 3, and there's our answer, sine of x squared plus 3 plus c. And we got it using substitution, converting a complicated integral to a simple one and working it out. Whenever you work out an integral, remember that you can check your answer if you're unsure by differentiating that answer and seeing if you get the integrand. So let's check that. Let's differentiate sine of x squared plus 3 plus c and see if we get cosine x squared plus 3 times 2x. So as a check, dx of sine of x squared plus 3 plus c would be, let's see, we got to use a chain rule here. Derivative of sine is cosine. Plug in the x squared plus 3 and multiply by the derivative of x squared plus 3, which is 2x. And of course, the derivative of c is equal to 0. So sure enough, when we differentiated our answer, we got cosine x squared plus 3 times 2x, and that's our integrand. So it checks back. We got a correct answer. Let's try another example. The integral of e to the power of sine of x times cosine x dx. Again, this is a complicated integral that doesn't match any familiar integration rule. So what we do is we look at this and think about what familiar integration rule this most closely resembles. Well, it's got e to the power of sine of x, so it looks somewhat like the integral of e to the u du. Now, if we're going to make a substitution that turns this into the integral of e to the u du, then that u should be the exponent of e. It should be equal to sine of x. So the substitution we're looking for here is u equals sine of x. And that's going to change this into the integral of e to the u, which looks good. But we've also got this cosine x dx we've got to deal with. We want to replace that with a du, but we've got to be sure that it really does equal du. So the way to check that is to differentiate u equals sine of x. You get du dx equals cosine of x. Multiply through by dx. You get du equals cosine x dx. And that tells us that this cosine x dx right here really does equal du. And now we can make those substitutions. This turns into the integral of e to the sine of x, which is the integral of e to the u. And the cosine x dx right here, it equals du. And look at that, a simple integral that we have a rule for. The integral of e to the u du is e to the u plus c. We now just have to plug in what u is equal to. It's equal to sine of x. And there's our answer, e to the power of sine of x plus c. We got it with substitution. If you're in doubt, you can check it. Let's differentiate our answer and see if we get our integrand, e to the sine of x times cosine of x. So dx of e to the power of sine of x plus c would be, let's see, we've got to use the generalized exponent rule here. That's e to the power of sine of x times the derivative of sine of x, which is cosine of x, and the derivative of c is 0. And this matches our integrand exactly. So it checks back. We did it right. Next example, the integral of x cubed plus x minus 1 to the power of 5 times 3x squared plus 1. A complicated integral that doesn't match any familiar integration rule. Let's see if we can use substitution to convert it to something simple. So we ask ourselves, what familiar rule does this most closely resemble? Well, it's got a power of 5 here, so you might think it looks something like the power rule. It looks like the integral of u to the 5th du, where u is x cubed plus x minus 1. That's what's being raised to the power of 5. So let's try that substitution. U equals x cubed plus x minus 1. And now all of this turns into the integral of u to the power of 5, which looks good. But then we also have the 3x squared plus 1 times dx. We're hoping that that turns into a du. Let's check it. We take the derivative of our choice for u here, du dx equals 3x squared plus 1, multiply through by the dx, and you get du equals 3x squared plus 1 dx. And now you can see that that 3x squared plus 1 dx really does equal du. So making these substitutions, we get the integral of u to the power of 5 times all of this stuff, 3x squared plus 1 dx, which equals du. So with substitution, we've converted this complicated integral into a really simple integral that we can evaluate using the power rule for integration. We get 1/6 u to the power of 6 plus c, and now we just plug in what u equals right here. So 1/6 x cubed plus x minus 1 to the power of 6 plus c. That's our answer, and we got it with substitution. Now quickly, let's check and make sure we really did it right. We take the derivative of this answer, and we want to make sure we get the integrand up here. So for this derivative, we'd have to use the generalized power rule. The 6 comes down, times the 1/6, that's a 1. And you get x cubed plus x minus 1 to the power of 6 minus 1, which is 5. Then times the derivative of x cubed plus x minus 1, which is 3x squared plus 1. And it exactly matches the integrand. So it checks back. We got the right answer. Next example. The integral of tangent fifth x times secant squared x dx. Let's see if we can use substitution to make this a simple integral. So we ask ourselves, what familiar rule does this most closely resemble? It's kind of complicated, but if you look here, you have a tangent of x to the power of 5. That's like a u to the power of 5. So you might think to yourself, this looks a little bit like the integral of u to the fifth du. And you could find that integral with the power rule. U here would be the thing that's being raised to the power of 5, which is tangent of x. So that's our substitution. U equals tangent of x. So this integral is turning into the integral of u to the fifth, but then it's multiplied by secant squared x dx, and you really want that to turn into a du, but you got to check and make sure that really works. So take the derivative of u equals tangent x, du dx equals secant squared x, multiply through by the dx, and you find that du equals secant squared x dx. And that exactly matches what we have right here. So good. We get the integral of tangent x to the fifth, which is u to the fifth, and the secant squared x dx is du. Looks just like what we had up here. We can use the power rule for integration to work out this simple integral, 1/6 u to the 6 plus c. And finally, you got to plug in what u is equal to. U is tangent of x. So this is 1/6 tangent of x to the power of 6 plus c. That's our answer. So you can see here how this complicated integral through substitution turned into a simple integral that we had a rule for. And again, you can check your work if you'd like to. You can take the derivative of this answer, and you want to make sure you get tangent to the fifth x, secant squared x. Make sure it matches that integrand up here. So let's check it. Let's take dx of 1/6 x to the 6, dx of 1/6 tangent to the 6x plus c, the derivative of our answer. And we've got to use the generalized power rule. The 6 comes down, cancels with the 1/6, and you get tangent to the fifth x times the derivative of tangent x, which is secant squared x. Had to use the chain rule there. And the derivative of c is 0. And sure enough, by taking the derivative of this answer, we get our integrand. So we know we did it correctly. It checks back. This next example has a little bit of a twist, so pay close attention. The integral of x cubed plus 3x to the power of 5 times x squared plus 1 dx. A complicated integral that doesn't match any familiar integration rule. So we're going to see if we can use substitution to convert this to a simple integral that we do have a rule for. Now, of course, looking at this, you see the x cubed plus 3x to the power of 5. And that suggests that this integral looks pretty much like the integral of u to the fifth du. So we're going to make a substitution to try to convert this integral into the simple integral u to the fifth du. Now what's being raised to the power of 5 in our integral is x cubed plus 3x. So that suggests we should make the substitution u equals x cubed plus 3x. And that's good because that turns this into the integral of u to the fifth, which is what we want. But then we have to make sure that what's remaining, the x squared plus 1 dx, really does equal the du that we want in our simple integral here. So as before, to check that, you take the derivative of your u, du dx is 3x squared plus 3, and you multiply through by the dx to get du equals 3x squared plus 3 dx. Now let's see if these substitutions work. First of all, this integral becomes the integral of u to the power of 5. And then we want a du right here. But be careful, that du does not equal x squared plus 1 dx. You don't have a match. Du over here, you can see, is 3x squared plus 3 dx. So this du, it's simply not equal to the x squared plus 1 dx. So you cannot replace the x squared plus 1 dx by du because it's not equal to du. So what can we do here? We have to deal with the x squared plus 1 dx. And that's not what we have here. But notice that we could multiply both sides of this equation by 1/3. And we get 1/3 du equals x squared plus 1 dx. And that tells us that the x squared plus 1 dx that we have here, it may not equal du. In fact, it doesn't. However, look, it equals 1/3 du. So instead of replacing this by the du that it's not equal to, we just replace it by the 1/3 du that it is equal to. And now that 1/3 is a constant, it can factor out of that integral. You get 1/3 integral of u to the 5th du. And we can use the power rule for that. This works out to be 1/3 u to the 6th over 6 plus a constant. We got to plug in what u is. It's x cubed plus 3x. So we get x cubed plus 3x to the power of 6 divided by 3 times 6 is 18 plus a c. So there's our answer. So this example serves to illustrate that you really do have to deal with the tail end of your integral and make sure that it's equal to du. And sometimes, as in this case, it might not be equal to du. You may have to do a little bit of algebra here to find out what this expression is in terms of du. And here, multiplying both sides by 1/3 told us that x squared plus 1 dx was 1/3 du. We made the replacement and everything went smoothly after that. This happens pretty often, so you want to work some exercises that are like this. Now before moving on, let's check this, make sure we really did it right. We want to take the derivative of our answer and make sure we get our integrand. So we do dx of x cubed plus 3x to the power of 6 over 18 plus c. Now, this is a constant of 1 over 18 multiplied by the x cubed plus 3x to the power of 6. We just use the constant multiple rule there. So the 18 stays on the bottom. Use the generalized power rule to differentiate the top. You get 6 times x cubed plus 3x to the power of 5 times the derivative of x cubed plus 3x squared plus 3. And now there's a 3 that factors out of the x squared plus 3, and that would multiply by the 6 to give you 18. Cancel with the 18 on the bottom, and this works out to be x cubed plus 3x to the power of 5 times x squared plus 1. And yes, it matches the integrand, so we did the work correctly. Next example, integral of sine pi x dx. This doesn't quite match any familiar integration rule, but it's awfully close. It looks a lot like the integral of sine of u du. So that means we should try the substitution u equals pi times x. So now this becomes the integral of sine of u. And then there's a dx, and we want to replace that dx with a du. But of course, we have to be careful to make sure that dx really does equal du. Let's do the differentiation. Du dx, that's the derivative of pi times x, that's just pi. And you get du equals pi times dx. So making the substitution here, you get the integral of sine of pi x is sine of u. And we want to replace this dx with the du. But be careful, it doesn't match. du does not equal dx. In fact, du is pi times dx. It's not dx. So we can't replace dx with du. So what will we do? Well, let's take our cue from the previous example. We could multiply both sides of this du equals pi times dx by 1 over pi, and we get 1 over pi du equals dx. So this dx that's right here, it doesn't equal du. In fact, as you can see here, it's 1 over pi times du. So let's replace it with what it's equal to. And now we can take that 1 over pi, factor it out, and we get 1 over pi integral of sine of u du. And this is good because we have a familiar integration rule for the integral of sine of u du. It's minus cosine of u plus c. So this gives us minus 1 over pi cosine u plus c. And we just replace the u with what it's equal to, pi times x. And there's our answer. This integral equals negative 1 over pi cosine pi x plus c. Now, I'm not going to do it here, but you can check it real fast, differentiate this, and you will find that you get sine of pi x. So it really does work out. Here's another example. It's complicated. The integral of 4x cubed plus 1 over 5x to the fourth plus 5x minus 3 dx. What are we to make of this? You might try a few things before you hit upon an idea that works. Split this up a little bit so it's the integral of 1 over 5x to the fourth plus 5x minus 3, and then times a 4x cubed plus 1 dx off at the end. Now we have the integral of 1 over a function. Imagine making u equal to 5x to the fourth plus 5x minus 3. This would be 1 over u. So this integral looks a lot like the integral of 1 over u du. So let's see if we could make a substitution that converts this complicated integral into this simple integral. Well, of course, what you'd want to do here, we just said it, you'd want to make u be equal to what's on the denominator. So u is 5x to the fourth plus 5x minus 3. Then you want to have this 4x cubed plus 1 dx replaced by du. But you got to check and make sure it's equal to du. It might not be. Take the derivative of u. You get du dx equals 20x cubed plus 5. Multiply through by the dx, and you get du equals 20x cubed plus 5 dx. So this expression right here that we want to convert to a du, well, it's simply not equal to du. Du does not equal 4x cubed plus 1 dx. As you can see here, it's 20x cubed plus 5 dx. Well, no problem. Multiply both sides of this equation, this du, by 1/5, and we get 1/5 du equals 4x cubed plus 1 dx. Now you can see this 4x cubed plus 1 dx right here. It may not equal du. In fact, it's not. It's equal to 1/5 du. So now we can make this substitution. This 1 over 5x to the fourth plus 5x minus 3, that's 1 over u. And what's remaining over here, the 4x cubed plus 1 dx, is 1/5 du. Factor out that 1/5, and you get 1/5 integral of 1 over u du. And we have an integration rule for integral of 1 over u du. It's ln of u. So 1/5 ln of u plus c. And finally, replace that u inside the ln with what it's equal to. And there's our answer. This integral equals 1/5 ln of the absolute value of 5x to the fourth plus 5x minus 3 plus a c. And I'm not going to do it here, but you can quickly check even in your head. It's a really simple computation. Take the derivative of this answer, and you will get this integrand. So it checks back. Our final example will illustrate something that's bound to happen eventually when you use substitution. Every once in a while, you'll make the wrong choice for u, and things just won't work out. When that happens, and it will, try a different u and keep doing it until you can get something that works. Think about the integral of e to the x over the square root of 1 minus e to the 2x dx. When you see this radical in the bottom, your experience with integration tells you convert that to a power. So doing so, we get the integral of 1 minus e to the 2x to the power of minus 1/2, and then times the e to the x times dx. And when you look at that, you have a very natural choice for u. This integral looks like the integral of u to the power of minus 1/2 du, so let u be equal to the 1 minus e to the 2x. But once we make that choice, we have to check and make sure that it leads to an expression for e to the x dx that converts to a du. So we have to differentiate u, and by the chain rule, its derivative is minus 2 e to the power of 2x. And here, let's next multiply both sides by negative 1/2 and also times dx. And we get negative 1/2 du equals e to the 2x dx. In our integral, the expression at the end is e to the x dx. And here we get e to the 2x dx equals negative 1/2 du. You'd really want to get an e to the x dx right here, so you could replace this e to the x dx in the integral with minus 1/2 du, but it just doesn't match. If only you could get rid of the 2 in this power, you'd have e to the x dx equals minus 1/2 du. You could replace this e to the x dx with that minus 1/2 du, but it just doesn't match, and there's no algebra you can do to get rid of that 2. So unfortunately, we have no match for e to the x dx. So when this happens, try something else. Let's regroup and take this same example from the beginning. We want to find this integral. This time, let's rewrite it differently. The e to the power of 2x right here, write that as an e to the x squared, which equals e to the power of 2x. And the e to the x on the top, scoot that over to the dx. So on the side here, you get e to the x dx. Now look at this integral. It should look familiar. It looks like the integral of 1 over the square root of 1 minus u squared du. And that's a familiar integration formula. That equals sine inverse of u plus c. So this suggests that maybe our u should be e to the x. So let's try that. Let's let u equal e to the x and follow the consequences of that choice for u. Du dx would be e to the x. So du is e to the x dx. And look at that. It exactly matches what we have here. So we now know that this e to the x dx can be changed into a du. So making these substitutions, the e to the x here changes to a u, and the e to the x dx changes to a du, and we've achieved our simple form. This integral, by a familiar integration rule, is sine inverse of u plus c. And we're almost there. Just plug in the e to the x for the u, and we get our answer. Sine inverse of e to the x plus c. So the kind of thing that happened here is normal with substitution. Even when you become experienced with it, sometimes you won't see the right u, and you'll make a bad substitution that doesn't work. That's normal. When it happens, try something else. That's it for today. In summary, we've learned about the substitution rule, how to make a substitution u equals g of x that could turn a complicated integral into a simple one. At this point, it's really important to work lots of exercises for practice. You should catch on pretty quickly to this, but it does take a little bit of practice and effort. In Lecture 44b, we'll look at more examples of substitution, and you may find if you're working the exercises and you get them all without any trouble, then you could probably skip Lecture 44b. We'll just look at more examples there. But in Lecture 44c, we're going to apply substitution to definite integrals. Today we were just talking about indefinite integrals. It also applies to definite integrals. So I'll see you next time, and goodbye.